This is a review of factoring polynomials. Remember that factoring a polynomial is when we take a polynomial and break it down into the product of smaller polynomials. To be completely factored, each piece must have no common factors and must not factor again using one of our techniques we're about to talk about below. Some methods to factoring polynomials. You don't just look at a polynomial and say, I think I know how this factors. You actually analyze it based on what do you notice, how many terms does it have. There is a method to which technique should you try. So the first thing we always check, no matter how many terms we have, is for a greatest common factor. Remember, that is something that divides equally into each of the terms. And we will then pull that out. It's kind of like reversing the distributive property, but we are pulling it out or factoring it out. To be a GCF for the whole polynomial, each term must have that as a common factor. After you've checked for the GCF, you need to then look at how many terms your polynomial has. If you have a binomial or two terms, you should check for one of the two following patterns: a difference of two perfect squares, and either that or a check for a sum or difference of two cubes. So what we mean by this, just to give you some reference point, is when we're talking about a difference of two perfect squares, we're saying that the parts that you're looking at are both perfect squares. So for example, x squared minus 9. X squared, it can be written as x to the second power, and then 9 is 3 to the second power. So notice that fits the a squared minus b squared pattern. And then the roots, the x and the 3, become the two pieces we use when we factor. So if you have two perfect squares with a minus between them, then that factors into the first root plus the second root and the first root minus the second root multiplied together. So two binomials, once with a plus, once with a minus. It is good to note that you cannot factor a squared plus b squared, because this would need to actually use imaginary numbers, which we haven't discussed yet. But for us, in the real numbers, this is prime. Now, for perfect cubes, you can factor perfect cubes regardless of whether it is a plus or a minus in between the two parts. So let's just do a basic example of what a perfect cube would look like. So let's say x to the third plus 27. That could be rewritten as x cubed plus, and 27 is a perfect cube as well. It would be 3 cubed. So again, my roots here are x and 3, but it's because they are perfect cubes. And then when we factor this, it factors into a binomial times a trinomial. The reason for that is that when you foil or not really foil, when you distribute all this out, you need to have enough things going on so that all the middle terms are going to cancel out, and you're just going to be left with the first pairing and the very last pairing. Now, the way to remember this pattern, it's a little difficult to just try to memorize a formula. It's always the roots that you get right here with the sign of the original problem. That's what goes into your binomial. And then we just do pairings of those two roots in this trinomial. The first pairing is the first one times itself. That's why it's a squared. The middle is the first root times the second root. And the last one is this very second root times itself. So notice it's just pairing those in groups of two. How do you remember the sign change? Well, we have a little phrase for that. It's called SOAP. That's where it works. So SOAP is same as the original, opposite to the original, and then always positive for the very last term. So when we say same and opposite, it's referencing the original problem. So notice that matches here. This is a plus because that's the original. This is a minus because that's opposite to the original. And this is a plus, which is the same as, or excuse me, because it's always positive. Same thing here with the minus sign. It's pretty much the same exact factoring, except now you have the minus in the binomial and the trinomial is all pluses. If you have a trinomial, we're going to look at how would you factor that. Now there's actually different techniques you would use for special cases, whether it has a 1 in front or not. You could talk about, is it going to be a perfect square trinomial, which is something we encounter a little bit later. To try to keep things simple, because you're going to be factoring a lot in this class, I'm just going to teach you one method that will factor all the trinomials that you encounter if they are factorable. So we're going to use the AC method, which is also known as factor by grouping. Factor by grouping is done when we have 4 terms, so we will discuss it as well in just a second, but we're going to set up factor by grouping to do the AC method. So the first thing you do is make sure your trinomial is in descending order and that the leading coefficient is positive. The reason we do that is it makes the signs for this work out the way we expect them to. If you do have a negative in front of your leading coefficient, I usually pull that out as a GCF of -1, regardless of if there's any other GCF. Once you've done that, you're going to multiply the a term, and what we mean by a term, remember, is that a trinomial is ax squared plus bx plus c. The a term is the leading coefficient when we're in descending order. So we multiply that a term by the c term, which is the constant, the one that doesn't have the x. Make a list of factors for this new product. So whatever we get for that, whether it be 24 or 36, whatever we get when we multiply a by c, and it could be a negative too, because c could be negative. So what we get, we write that down. We make a list of the factors. If your a times c was greater than 0, in other words, positive, your factors that you pick need to add to the middle term b. If your ac is less than 0 or negative, your factors need to subtract to the middle term b. We replace the middle term with the two factors we found in part 3, so that's going to look like this. You're going to have ax squared plus something x, and these could be negatives, we don't know, and then plus our c. So now you have two terms in the middle instead of just one. It's going to split. And that creates the 4 terms you need for factor by grouping. So now we're going to discuss factor by grouping as its own technique. So this would need to still be finished. So factor by grouping happens when you have 4 terms. You group the term, and again, all of these techniques are ways to attempt to factor. We do not have a guarantee that everything factors. So we're going to group the terms into 2 groups of 2 terms each, so that each has a group of each of the groups we make has a common factor. So maybe they have an x in common, or they're both divisible by 2. We factor out the GCF for each individual group. If there is now a common binomial, so that's going to be the parts you've left in the parentheses, then we factor that out to the front, and then our remaining pieces are our second binomial. If we do not get something that has a matching binomial factor, then that means that we're probably not going to factor, but a good thing to do is to try to rearrange the terms and try the steps again. Now, after you've tried one of these techniques, whether you had 2 terms, 3 terms, or 4 terms, make sure that your resulting factored polynomial is completely factored. What that means is that inside each parentheses, there are no common factors that can be pulled out. So you can't have that 2 things inside the same parentheses are divisible by 2, or that they both have an x. And then make sure that you don't have any polynomials left over that actually factor using other methods. And we're going to see one in just a second that does that. And do remember that not all polynomials factor, so it is possible that you can have a polynomial that does not factor at all. If that happens, we call it a prime polynomial. A misconception a lot of students have is when they pull out a GCF and then nothing else happens after that, they want to call that a prime polynomial. Technically, if you are able to pull out a GCF, you're not a prime polynomial. You used one of the techniques. So just remember that. The prime means you can do absolutely nothing. And you can talk about a parentheses by itself being prime. It doesn't mean the whole problem was prime. But when we break it down, we should have a group of prime polynomials all multiplied together. Excuse me. So we're going to look at this first example here, and there's just a quick typo. Let me fix that. So this is 8x to the third minus 27. So things that we should look at. Okay, first of all, is there a GCF? We should always check that first. 8 has factors of 1, 2, 4, and 8. Only one of those that divides into 27 evenly is 1, and pulling out a 1 doesn't really help us. So this has no GCF. Also the x's, there's x's on the first one but not on the second one, so they don't share a common x. So then this is a binomial because there's 2 terms, and then we need to talk about, is this possibly perfect squares or perfect cubes? So looking at this, 8 is not a perfect square. Remember, perfect squares are something times itself. So 8 is not anything times itself. 27 is also not a perfect square. They could possibly be perfect cubes. In fact, 8 is 2 cubed, and 27 is 3 cubed. We also need to remember that in this one we have an x as well. This is x to the third. So this first term is 2 and x both cubed, and the second term is 3 cubed. So we're looking at perfect cubes that are separated with a minus. So let's go ahead and think about what that's going to look like using our SOAP to help us remember our signs. So we're going to have same as the original for the first sign in between the two binomial pieces, and then it's going to be opposite to the original for the first sign after this first term in the trinomial. And then remember, the last sign before the last term is always positive. So we kind of already know what the structure of our problem should look like. These roots are going to help us figure out the rest of this pieces. So for the very first part in the binomial, you just write the exact things that were the roots. So this is going to be a 2x and a minus 3 now. For this, we do remember pairs of these two roots. So this is 2x times 2x and 2x times 3 and then 3 times 3. So we work this out. This is 4x squared. This would be 6x and 9. So my final factored form, because as long as you haven't left out a GCF of any kind, this trinomial should no longer factor in a perfect cube formula, is 2x minus 3 times 4x squared plus 6x plus 9. Okay, let's look at my second example here. This has a GCF because 8 and 50 are both divisible by 2. So we're going to start off by pulling out the GCF of 2. So you pull it out as if you were undistributing here. So this would be 8 divided by 2 is 4. Then I still have my x squared. Negative 50 divided by 2 is negative 25. Now, that doesn't mean we're done because we need to analyze what's left in that binomial. This is two terms, so that means it could possibly be one of the perfect square or perfect cube patterns. And it looks like this one's going to be perfect squares because 4 is 2 squared, and that would be x squared, so that's a 2x, and 25 is 5 squared. So remember, if you have perfect squares, they have to have a minus sign in between them for us to be able to factor using the pattern. And the pattern is that we write those two roots, once with a plus and once with a minus. So this would be 2x plus 5 and 2x minus 5. Do not forget that there is also a 2 out front. Your GCF is still part of your final answer. It's just a coefficient out to the front. Okay, let's look at example 3. So 1, negative 13, and negative 30 do not have a GCF. They don't all have an x, so we can't pull anything out that's a variable. So we're looking at 1, 2, 3 terms. So this is a trinomial. So we're going to use the AC method because, again, you could factor this one faster, but we're trying to just keep it one method to keep it simple. So the AC method, which says you need to multiply the A term by the C term, so that's 1 times negative 30. So when it's a 1 in front, you essentially just get C, so that's negative 30. We list factors of negative 30, which I don't worry about the sign placement yet. I just list my factors. So I always start with 1 and break it up into what goes into 30 evenly. So 1 times 30 is 30. 2 times 15 would be 30. 3 times 10 is 30. 4 does not go evenly. And then 5 times 6. I know that this is the whole list because it goes from least to greatest as I go around, and 5 and 6 have nothing in between them that could possibly go into 30. You should always check the last two factors to make sure nothing in between them could go into 30. And they're back to back, so there is nothing. So then when we pick our factors, we have to be really careful. If you're dealing with a negative for your AC, we need to subtract to the negative 13 in the middle. So if we do 1, and obviously if it's a negative, that means your right column is going to be negative. Your bigger column always defaults to the sign in the middle when you're doing different signs, because essentially a negative in the C position means different signs, because that's the only way you can multiply to make a negative. So this would be negative 29 if we subtract. This would be negative 13, so this looks like the right pair. This would be negative 7. A lot of people will pick 3 and 10 because they say that makes 13. But because of our sign on our AC, we're not adding to 13, we're subtracting. So there is a pair that makes negative 13. So then we make this 4 terms by splitting the middle into the 2 terms that we just discovered, which is a 2x and a negative 15x. Take care to make sure that this variable always shows up on those 2 parts that got split. And then we factor by grouping. So to factor by grouping, you make 2 pairs and you pull out what they have in common. This first pair has an x in common, so I'll have x plus 2 left over. The second pair leads with a negative. Whatever this sign that this leads with, you pull that out, and then they're both divisible by 15. So negative 15 divided by negative 15, and then there's an x, so that would just be x, and then negative 30 divided by negative 15 is positive 2. If this is going to factor, then you should have a matching binomial there, and we do. It's both of them are x plus 2. So we can see that. And then we pull that out to the front as a GCF, and then the leftovers, the x minus 15, becomes our second binomial. Now I know you could probably have factored this one quicker, but like I said, we're just trying to keep a simple pattern for all of them. So let's look at number 4. I did the same exact problem, except I changed this to a plus sign in front of the 30. So when I go to do a times c, it's 1 times 30, so it's 30. This time we're going to be adding to the 13 in the middle, and it's still a negative 13 in the middle. The reason we're adding is because our AC is positive. So then we're going to have 1 and 30 again, 2 and 15, 3 and 10, 5 and 6. When you add to the number in the middle, you're going to have the same sign in both columns, and the sign is dictated by the sign in the middle. So everything's going to be negatives here. So if this number appears positive, all signs are going to be the same in your list. So it looks like the pair that adds to negative 13 this time is negative 3 and negative 10. So we do our split into 4 terms. So this has been split. And then we factor out our GCF in our 2 pairs. So this would be x times x minus 3. I pull out the leading sign there, and then they also have a 10 in common. And this 30 divided by negative 10 would make that negative 3. So we do have a match in our binomial. And then remember, the leftovers in front of that make the second binomial. So this would be x minus 3 and x minus 10. Okay, let's look at our next example. This one is a little bit more difficult because we've put a number in front that's not a 1, but we can still attack it using the same method. So we do 4 times negative 5, so that's our AC. So that's going to be negative 20. And then we list factors, 1 and 20, 2 and 10, 3 doesn't go, 4 and 5. Because this is a negative AC, remember we're going to try to subtract to the middle term. The middle term here is a positive 8. So because we're subtracting and getting a positive, that means our bigger column is plus and our smaller column is minus. Because notice these are all the smaller of the pairs and these are the largers. So this makes 19, that makes 8. And the last one is a positive 1. So it looks like we're going to be going with negative 2 and positive 10. Now, you really don't have to put the first one first. You can put 10x first if you want, but I just usually write them in the same order. Or if I see a specific reason to pair something, I will pair it a certain way. You just need to make sure both middle terms are represented with the correct signs. Okay, so in our factor by grouping, we will pull out a 2x, and that would leave me with 4 divided by 2 is 2. X squared take away 1x is still x. Negative 2x divided by 2x would be negative 1. In the second pair, we lead with a positive, so we'll pull that out, and they're both divisible by 5. 10 divided by 5 would be 2. We still have the x. Negative 5 divided by 5 is negative 1. I do have my matching binomial, so I have 2x minus 1, and my leftovers are the 2x plus 5. Okay, so we have example 6 next. Again, a trinomial, no GCF that we can pull out because there's not something they're all divisible by, so we have to do our AC method. So 16 times 9 is going to be a little bit larger. So when we multiply this together, we are going to expect a bigger number, which means we may have more factors that we have to list. That doesn't mean this is a bad method. It's just going to take a little bit longer than it would if you knew some tricks. So 16 times 9 is 144, so it's going to be a big list. So 1 and 144. If we divide that by 2, that's 72. Let's see if 3 goes into it evenly. 3 and 48. And I'm just dividing on my calculator as we go just to check. So 144 divided by 4 is 36. If you get a decimal, you know it doesn't go evenly because 144 will not divide evenly by 5. If we divide it by 6, we get 24. If we divide it by 7, we get a decimal, so that doesn't work. If we divide it by 8, we get 18. Notice these are getting closer and closer together. If we divide by 9, we get the 16, because remember, that's how we got it. 10 does not go into it evenly because it does not end in a 0. 11 does not go into it evenly, and then the final one is 12. So 12 times itself. Notice that's the end of the list because there's nothing in between 12 and 12. We're supposed to, because this is a positive AC, we're supposed to add to negative 24. So that means everything's going to have to be negative if we're going to add and get a negative sign. And if you look, it ends up being the very last pair. So if we hadn't made our whole list, we wouldn't have got this. The reason that happens is because the first term and the last term are both perfect squares, and the middle term is those two square roots doubled, essentially, after you multiply them together, because this would be a 4 and a 3, which is 12, and then you double it and you get 24. You didn't need to know that to be able to factor this, but this is actually something called a perfect square trinomial. So that's actually important for us in a later version of what we are going to do with some trinomials. So you can factor it this way, but it is good to know that that's why this ends up being the same number in the middle. So this is 16x squared minus 12x, and then plus 9. We pull out our GCF. For 16 and 12, we can pull out a 4. They both have an x. That would leave it with 4x, and then 12, that would be minus 3. We need to pull out a negative for this first pair. And then notice 12 and 9 are both divisible by 3. So this is also going to give me 4x and then negative 3 because we're dividing out a negative. That means we change our sign. So then notice this is a little bit tricky for some people because you do get your match, but your leftovers are also the same as your match. The yellow, remember, becomes one binomial out in the front. It's like a GCF that we pull out. The blue, the leftovers, become the second one. And so we get the same binomial twice. A shorthand of that would be 4x minus 3 squared. Some people might be technical and say you have to write it this way. Some people are okay with you writing it in an expanded form where you just have it listed twice. Just check with your instructor on what their preference is. And then the final example here is a 4-term problem. So let's check for a GCF first. It looks like 3 divides into everything and they all have at least an x. So we're going to pull out a GCF of 3x. That would leave me with x to the third minus 2x squared minus 3x and then plus 6 and no x. Okay, so then we would see about working this out further. So we're focusing now on just the part inside. This is 4 terms because I think this might factor again. So we're going to factor by grouping. Keep the 3x out front, just keep that there. So this would be an x squared we can pull out of the first pair. So then that would leave us with x minus 2. The second pair, we can pull out a negative and they both are divisible by 3. So that also leaves me with an x minus 2. And then this is a match inside. So 3x would have x minus 2 come to the front. And then the leftovers are x squared minus 3. So this is where you would need to be careful because notice we do get something that has an x squared still and a minus sign, but the second part of that is not a perfect square. So if that had been x squared minus 4, we would have been able to factor this again. We would have actually been able to break up the inside. But since it's not factorable here. This is not both perfect squares. So this is 3x, x minus 2, x squared minus 3. Completely factored. All right, and that is the end of this tutorial video.